Welcome back to The Explainer. Okay, let's just dive right into this. If you're preparing for your Cambridge IGCSE Mathematics 0580 exam, you probably already know that geometrical transformations can sometimes feel, well, like a puzzle with missing pieces, right? You look at a shape, you look at where it ended up, and you somehow have to describe exactly how it got there. It can be super frustrating, but today we're going to completely demystify this. We are pulling directly from the source material to lock down the exact rules, the precise vocabulary you need, and those hidden traps that trip up so many students. Get ready to master transformations once and for all.
So, here is our roadmap for today. We'll start with the language of transformations, move into reflections and translations, break down the rules of rotation, tackle enlargements and scale factors, and finally, wrap up with describing and combining transformations.
Section 1. The language of transformations. Now, what's really interesting about this is how simple these core terms actually are once you just isolate them. When a shape is transformed, your original starting shape is always called the object. The new shape it turns into, that's the image. So we literally say that a transformation maps the object onto the image. Next up, we have the word congruent. If a transformation keeps the shape the exact same size and the exact same shape, boom, the object and image are congruent. And finally, we have invariant. This is a fantastic word to keep in your back pocket. It refers to anything, like a specific point, that stays exactly the same and absolutely does not move when a transformation happens. It's like the ultimate stubborn point.
All right, moving on to Section 2, Reflections and Translations.
Take a good look at that mirror line labeled PQ right there. In a reflection, corresponding points on your object and your image are the exact same distance from the mirror line, just on opposite sides. Notice how point A on the green triangle is a certain distance from the line, and its image, point A prime on the yellow triangle, is that exact same distance away on the other side. The object and the image are congruent, but, and this is absolutely crucial, the image is reversed. The source material offers a really great tip here. Instead of just counting squares on the grid, you can actually trace the shape and the mirror line, turn your tracing paper over, and line it back up. And hey, if you have a sloping mirror line, just physically turn your page so the line looks vertical to you. It makes checking your reflection so much easier.
Okay, let's slide over to our next transformation, translation. In a translation, every single point on the object moves the exact same distance in the exact same direction. For example, look at triangle A. It maps onto triangle B by moving 6 squares to the right and 4 squares down. And we describe this mathematically using a column vector. The top number is your horizontal movement. Positive means right, negative means left. The bottom number is your vertical movement. Positive for up, negative for down. So right here, our vector is 6 over negative 4. My biggest piece of advice, just pick one specific corner on the object and count over to that exact corresponding corner on the image. Whatever you do, don't mix up your corners.
Section 3. The rules of rotation.
You know, it's really helpful to contrast a reflection with a rotation side by side. On the left, we have our reversed reflection. But on the right, look at the rotation of shape P. When an object is rotated, it turns about a specific point. But unlike a reflection, the object and the image are the exact same way round. They aren't flipped, they aren't reversed. You can literally just spin your paper to see how the object maps perfectly onto the image.
So here is the crucial point for your exams, this 3-part checklist. To fully describe a rotation, you absolutely must provide 3 parameters. Step 1, the angle of rotation, like 90 degrees or 180 degrees. Step 2, the direction, meaning is it clockwise or anti-clockwise. And step 3, the center of rotation, given as a specific coordinate. Listen, if you miss even one of these 3 things, you will drop marks, no question. And again, you can use tracing paper here. Trace the shape, put your pencil point firmly down on the center of rotation, and just spin the paper.
Section 4. Enlargements and scale factors. This is where things get really interesting.
Let's look at how this works visually. Right here, we have an enlargement by a scale factor of 3, with the origin as our center of enlargement. Now, a positive scale factor of 3 obviously means the image is 3 times larger, but remember, it also dictates distance. Every point on the image must be 3 times as far from the center of enlargement as the corresponding point on the original object. The scale factor is literally the number you use to multiply those lengths. Now, examiners absolutely love to test your understanding by throwing in fractional and negative scale factors. It's super easy to confuse them, so let's separate them clearly right now. If you have a fractional scale factor, so something between 0 and 1, like 1/2, the image actually shrinks. It becomes smaller than the object, even though mathematically speaking, we still call the transformation an enlargement. Weird, I know.
On the other hand, if you have a negative scale factor, two wild things happen. First, the image is inverted, meaning it's turned upside down, and second, it gets thrown to the completely opposite side of the center of enlargement. It's almost like it's been banished to the upside down.
Let's really anchor that concept with the visuals from our source. On the left, we have a scale factor of 1/2. See how the red triangle is half the size and half the distance from the origin? Okay, now on the right, we have a negative scale factor of -2. Notice the center point O. The original object is below it to the left, but the image is thrown to the opposite side, above it to the right. It's inverted, and it's twice as large. And if you look closely, the lines connecting the corresponding points literally pass straight through the center of enlargement.
So what happens if an exam throws a curveball and asks you to find the center of enlargement when you only have the two shapes? Well, you solve it visually. Step 1. Take your ruler and join the corresponding corners of the object and the image. Step 2. Just extend those straight lines outwards. Step 3. Find the exact point where all those lines intersect and cross each other. That right there is your hidden center of enlargement. Honestly, it's a highly satisfying technique once you actually try it.
All right, our final section, Section 5, Describing and Combining Transformations.
Okay, this slide, this is your ultimate high-yield cheat sheet directly from the source material. If a question asks you to describe fully a transformation, just stating the name is only the very first step. If it's a reflection, you absolutely must provide the equation of the mirror line, like y equals x. If it's a rotation, you have to give the angle, the direction, and the center. Translation, you need the column vector. And if it's an enlargement, you must state both the scale factor and the center of enlargement. Seriously, memorize this table. It maps directly to the examiner's marking scheme.
Sometimes, an exam will give you a combination of transformations and ask you to describe the single transformation that achieves the exact same result. Look at example 42.11 right here. Triangle A is rotated 90 degrees clockwise to become triangle B. Then, B is reflected in the y-axis to become triangle C. But the question asks for a single transformation from A to C. The textbook gives a major warning here, guys. If they ask for a single transformation, you must not simply list a combination. You've got to step back, look at A and C, and realize that turning A over to fit perfectly onto C makes it a reflection. So in this specific case, the single transformation is just a reflection in the line y equals -x.
Okay, let's quickly summarize these core visual rules to really solidify your attention before we wrap up. Translations, rotations, and reflections keep the shape exactly the same size. They are congruent. Enlargements change the size, so they are similar. Remember that fractional scale factors actually shrink your shape, while negative scale factors invert it and push it to the opposite side. And always, always use extended lines crossing each other to find that sneaky center of enlargement.
I want to leave you with a bit of a provocative thought directly from the source material. When combining transformations, does the order actually matter? Think about it. If you rotate a shape and then reflect it, is that the exact same result as reflecting it first and then rotating it? Well, the textbook warns us that it usually makes a big difference. The math notation works just like functions. Order absolutely matters. But don't just take my word for it. I highly encourage you to grab some tracing paper after this explainer and test it out for yourself. See you next time.